Welcome to Recursion. In this chapter, we will explore the concept of recursion and how it can be used to solve complex problems. Recursion is a powerful technique in programming where a function calls itself to solve a problem. It involves breaking down a problem into smaller subproblems until a base case is reached. Recursion provides an elegant and intuitive way to solve certain types of problems. So, let's dive in and understand the world of recursion. Understanding recursion and recursive functions. Recursion is a programming technique that allows a function to call itself. It breaks down a complex problem into simpler subproblems until a base case is reached. Recursive functions are the building blocks of recursion. They utilize the call stack to keep track of function calls and their corresponding variables. Recursion provides an elegant and powerful way to solve problems that exhibit self-similarity or have repetitive structures. By understanding recursion, you will expand your problem-solving abilities and unlock new approaches to tackle complex tasks. Recursive versus iterative approaches. When solving problems, we have two main approaches, recursive and iterative. Recursive approaches involve breaking down a problem into smaller subproblems and solving them recursively. They often use function calls and the call stack to manage the process. Recursive solutions can be concise and intuitive, as they closely mirror the problem structure. However, they may have higher memory usage and can lead to stack overflow if not carefully managed. On the other hand, iterative approaches use loops to repeatedly execute a block of code until a certain condition is met. They typically require explicit variable management and iteration control. Iterative solutions are generally more efficient in terms of memory usage and performance, as they avoid the overhead of function calls and stack operations. However, they may result in more complex code, especially for problems that have a recursive nature. Examples of recursive algorithms. Let's explore a couple of examples to understand how recursion works. The first example is the factorial function, which calculates the product of an integer and all positive integers below it. The recursive definition of the factorial function is factorialn equals an asterisk factorialn 1. The base case is when equals 0, where the factorial is defined as 1. Another famous example is the Fibonacci sequence, where each number is the sum of the two preceding numbers. The recursive definition of the Fibonacci sequence is Fibonaccian equals Fibonaccian 1 plus Fibonaccian 2. The base cases are Fibonacci 0 equals 0 and Fibonaccion equals 1. These examples demonstrate how recursion can elegantly express complex mathematical patterns and relationships, providing efficient solutions to such problems. Handling recursive algorithms efficiently. While recursion is a powerful technique, it's important to handle recursive algorithms efficiently. Two strategies can help optimize recursive algorithms: tail recursion and memorization. Tail recursion is a special type of recursion where the recursive call is the last operation performed in a function. Some compilers and programming languages can optimize tail recursive functions by transforming them into iterative loops, eliminating the need for additional stack frames. This optimization helps prevent stack overflow and improves the performance of recursive algorithms. Memorization is a technique that optimizes recursive algorithms by caching the results of expensive function calls. It involves storing previously computed results in a cache to avoid redundant calculations. Memorization is particularly useful for recursive algorithms with overlapping subproblems, as it can greatly reduce the overall computation time. By applying these optimization techniques, we can enhance the efficiency of recursive algorithms and make them more practical for real-world applications. Congratulations on completing this chapter on recursion. Recursion is a powerful technique that allows you to solve complex problems by breaking them down into smaller subproblems. By understanding recursion and recursive functions, you gain a valuable tool in your problem-solving arsenal. We explored the differences between recursive and iterative approaches and saw how recursion can provide elegant and intuitive solutions for problems with repetitive structures. The examples of factorial and Fibonacci sequence demonstrated the beauty and efficiency of recursive algorithms. Remember, when working with recursive algorithms, it's important to handle them efficiently. Techniques like tail recursion and memorization can optimize recursive functions, improving their performance and avoiding stack overflow. Now that you have a solid understanding of recursion, you can apply this technique to a wide range of problems and expand your programming capabilities. Keep practicing and exploring the possibilities of recursion in your coding journey. Thank you for joining us in this chapter, and stay tuned for more exciting topics in our programming series. Don't forget to subscribe to our channel and press the bell icon to receive updates and notifications for future content.